Okay. So at this point, we will um, end up this topic 4, this our topic on infinite series with a discussion on Taylor and Maclaurin series. Okay. So in the previous lesson, we were able to derive power series for several functions using geometric series. Okay, with term by term differentiation or integration, and sometimes we also did some operations like addition, composition of functions, okay, and other operations, okay. Now, in this lesson, we will study the general procedure for deriving the power series for a function that has derivatives for all orders. Now, the following theorem gives the form that every convergent power series must take. Okay, so in theorem 22, this states what form or how do we write a convergent power series. Okay, so as you can notice that here, if f is represented by this power series, okay, then f of x is actually this series, okay, it's actually this series. So um, this is basically if you actually write this in a compact form, okay, that basically is the the sum of f the nth derivative of c over n factorial for times x minus c raised to n for n equals 0 up to infinity. We will just make it clear that when you have f the zero derivative, okay, the zero derivative of your function, okay, the zero derivative of the function at c means the value of the function at c, which means we will not, the zero derivative means we will not take any derivative. Okay, that is the meaning of that. Because we don't have any meaning with this, we really did not have any definition for the symbol. Okay, so we define it as basically your the zero derivative or your function, okay, or zero order derivative, or basically your function itself. Okay, so now this might have been these few terms might have been familiar with you as well as this one. Okay, because this is what we have studied in a previous lesson. We call this the Taylor polynomial. Okay, but later on, I will after defining what a Taylor and Maclaurin series is, I will differentiate it with the Taylor polynomial. Polynomial. Okay. So let's define what a Taylor and Maclaurin series is. Okay. So a Taylor series has this form. Okay. And again, as you can see, we will be familiar with these terms. Okay, because this is again um similar to what we had in the when we studied Taylor polynomial. And if we actually set this equal to 0, then we will have what we call the Maclaurin series. Okay. Which again is a familiar would be familiar with you because we also have studied Maclaurin polynomial. Okay. What's the difference between Taylor series and Taylor polynomial? Taylor polynomial is basically um, a finite series. Okay. Taylor polynomial and its counterpart, Maclaurin, a special case, sorry, it's a special case, Maclaurin polynomial, are finite series. Basically, they are finite series. We just use a few terms of these polynomials in order to approximate. Okay, you remember that we call this Taylor or Maclaurin polynomial as approximating polynomial. Okay, we call them as polynomials that approximate our function. So the purpose of the Taylor polynomial and the Maclaurin polynomial is to approximate your f of x. That's why we call them approximating polynomial p. Okay, p of n. So n here indicates how many or what degree or what order our approximating polynomial is. So those are that is your Taylor polynomial and Maclaurin polynomial. These are different from Taylor series. Okay, from Taylor series and Maclaurin series. Okay, in a sense that these two, Maclaurin series, in the sense that these are infinite Okay, infinite series. And their primary purpose, primary purpose is to exactly represent f of x. Okay. You would write a Taylor series or a Maclaurin series as an infinite series because you would like to exactly represent your f of x. Okay. So that's the difference. That's the fundamental difference between a Taylor or a Maclaurin polynomial and a Taylor or Maclaurin series. Okay. So you should be aware of that difference. Okay. So here we will be studying the Taylor series and Maclaurin series, in which the purpose is for us to have an alternate representation, or that we can write your function, okay, whatever function it is, into a series of terms, or a power series basically. Okay. We would like to represent it as an infinite power series. Okay. So um we representing your f of x as a series, or in another way, using a power series, or actually, yeah, a power series is actually one of the ways, okay, in which we can actually re-express your f of x in another form. Okay, we will do that actually in the future, wherein when we study, for example, Fourier series. Okay, Fourier series is another way to represent your f of x, okay, or your function, okay, but in another way naman, okay. So we'll talk about it. We'll talk about your Fourier series in the next topic, okay, after topic 5. Okay, so basically, Taylor series and Maclaurin series would represent your f of x in terms of an infinite power series. Okay, so in this particular lesson, we will devise the formal methods on how to do that. So how do we represent f of x into an infinite power series, and therefore write the Taylor or Maclaurin series representation? Okay. So um, if you can remember, example 38 in lesson 4.7, we have found a fourth order Taylor polynomial for ln of x centered at 1. Okay, so we had this as your example. We have this as the result of your example 38. Okay. Now, if we actually add all of the terms, okay, all of the terms of this, okay, actually, this is just a fourth order polynomial. We can actually extend it to contain infinite number of terms. So we can basically add the nth term, okay, for that. Okay, and following the pattern, as you can see, for say let's have this to be when n equals 1. So when n equals 1, okay, your term becomes x minus 1. Okay, when n equals 2, you have here as negative 1 half x minus 1. Okay, squared. Okay, squared. Okay, when n equals 3, you have here 1/3 x minus 1 cube. And then when n equals 4, okay, you have negative 1/4 x minus 1 to the fourth. If we can actually find a pattern around these first few terms, then we can write the nth term for this function. Okay, that is your f of x equals ln of x, which is centered, okay, at x equals 1. Okay. So as you can see, first of all, you have your sign. Okay, so this is an alternating series, basically, with all the odd terms positive and even terms negative. Okay, so that means you could use, okay, the factor negative 1 raised to n would be a useful way to represent that alternating signs. Okay, and if you can check, if n is odd, this is negative. Okay, which is not the case here, because when n is odd, this should be positive. So we can add either we can subtract 1 or we can add 1. Okay, depending on the mathematical convenience. I'll say that we can subtract 1 here na lang, but equally valid is to add 1 there. Okay. So what happens when we subtract 1? If n is 1, that becomes 1 minus 1. So that becomes 0. I mean, n minus 1 becomes 0. So therefore, negative 1 raised to 0 is positive 1. So that is a positive. Okay. When n is 2, that's 2 minus 1. So that becomes 1. Okay. Negative 1 raised to 1 is a negative number. Okay. So this factor now with an exponent of n minus 1 now captures your sign. Okay. Now can represent now the sign change. Okay. That odd terms carry a positive sign while even terms carry negative sign. So we'll use this. Again, the choice of this being n minus 1 or n plus 1 depends on the mathematical convenience of your representation. Both are equally valid, both are correct, okay? But one may be convenient over the other. Okay, so in this case, since we are working on finding the nth term of ln of x without any context, we'll just arbitrarily choose n minus 1 here. Okay. Of course, all of them would contain x minus 1 as a factor. So we will have it as x minus 1. Now, with regards to the exponent of x minus 1, you see that this is actually equal to n. Okay, when n is 1, the exponent is 1. When n is 2, the exponent is 2. When n is 3, the exponent of this is 3, and so on. So we'll simply have this as over n. And then finally, this number. Okay, this number here. That's the number at the denominator. Okay, so basically, we'll divide it with a number. And as you can notice also, if we write this as 1 over 1, you'll notice that that number in the denominator is also equal to n. Okay, so we'll have it here. Okay, so you can check, say for example, for n equals 5, this should be 1/5 positive, okay, times x minus 1 raised to 5. That should be the pattern that we are following. Now, you can check it if you can obtain it from here. Okay, so that. Okay, so that. We can represent now your ln of x, okay, in terms of its polynomial, in terms of its Taylor series centered at x equals 1. Okay, so how do we do that? We add, okay, we sum up the n term. Okay, so summing up n terms, we have negative 1 raised to n minus 1 multiplied to x minus 1 raised to n over n. Okay, for n equals 1, remember that we will be starting our n from 1. Okay, and then we will add infinite number of terms of that, which will give us the expansion would give us something like x minus 1, okay, minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed, okay, plus minus 1/4 x minus 1 raised to 4, okay, plus 1/5 x minus 1 raised to 5. And then we write the general term as negative 1 raised to n minus 1 times x minus 1 raised to n over n, and so on. So this is now, okay, what we have written here, okay, what we have written here is the Taylor Taylor series, okay, this is now a Taylor series, okay, of ln of x with centered, okay, centered at x equals 1. Okay, that's the Taylor series of your ln of x centered at x equals 1. Okay, so this is not a Taylor polynomial anymore because we're adding infinite number of terms. That's why this is now called a Taylor series. Okay, so now there is a question here whether this series would actually converge. Okay, whether the series would actually converge. So actually, aside from that, okay, aside from that question that asks whether this series would converge, another question that we have to settle is that after settling that first question, so even if we determine that this is actually a convergent series, the question is, if, does this converge to ln of x? Okay, does this converge to ln of x? So the first question is the series convergent? Number two, even if the series is convergent, okay, if the series is convergent, is that series convergent to the function it represents? Okay, so those are the two questions that we need to address after writing your Taylor series. Okay, and we will have a discussion on that later on. Okay, so let's have some more examples. Okay, so there. See that the example here use n plus 1. Okay, I use n minus 1 there. Both are okay. Okay, again, I remind, both are okay. It depends on the on which expression is more convenient on you. Okay, as long as you would be able to arrive at the correct sign. Okay, at the correct sign. Okay, so there. Now let's try to work on example 57. Let's use the function f of x to form the Maclaurin series, okay, and determine the interval of convergence. Okay, so Maclaurin series, again, is centered at 0, at x equals 0. X equals 0. So it means now that um, what we will do is to get these successive derivatives. The procedure is actually the same procedure that we have been employing in determining the terms of your Taylor polynomial, with the exception that after finding, okay, number one, you have to find sufficient number of terms to be able to discern a pattern. Okay, so that's the difference between this and finding a Taylor polynomial. Finding a Taylor polynomial would require you to find a certain number of terms depending on the accuracy that you would like to have you would like your approximation to have. Okay. But here, the number of terms should actually depend on you being able to discern a pattern so that we can get a general term. Okay. So here, let's try to find eight including the original function itself. Let's try to find seven derivatives. Okay. Anyway, you would be observing that the derivatives would actually follow a certain pattern later on because this is a sine function. Okay. So you can verify this differentiation or derivatives. Okay. Um, and that the derivative of your sine actually rotates from sine to cosine to negative sine to negative cosine, and then back to sine to cosine to negative sine then to cosine. So every after the third derivative, the pattern is repeated. Okay. Pattern includes the function itself, no? Okay. So after getting the derivative, okay, you obtain the values of the function and its derivatives. Okay, at x equals 0, since this is the center. Okay, this is the center of your. Okay. This should have been C eh. Okay, this should have been C. Sorry. Yung center niya dapat nasa C kasi. Okay, anyway, X or C, as long as we are on the understanding that this is the center. So it's either we express our center in terms of C, okay, because that is f of C technically, okay, or we express it in terms of X because eventually our X would be equated to C because that's the center, okay, so which is 0. So this is basically we consider them to be the same. Okay, so whether you say it's the center is at x equals 0 or c equals 0. Okay, I think we will not be faulted on that. Okay. So now as you can see, that there are terms or there are derivatives, there are function values and derivatives that are 0. The function value itself is 0. Okay, as well as the second, the fourth, and the sixth derivative. It seems that even derivatives are 0. And actually, you can extend that to the function value, considering that the function is or can be considered as the 0 order derivative. Okay, if you consider that the function itself is a 0, okay, 0 order derivative. Okay, you can actually say that even derivatives are 0, including this 0 order derivative. So which means we will be able to form only, um, and if you actually look at this pattern, okay, if you actually look at this pattern, this is, this is your, 0, okay, 0 order derivative. This is your second order derivative. This is your fourth order derivative, and so on. So all of these are 0. Okay, all of these are 0. What remains are the odd terms. Okay, what remains are the odd derivatives. Okay, so we can, work on that and say that, so this is for sine, no? Um, we will have, f prime of 0, okay, equals f prime of 0 is 1, okay, f prime of 0 is 1, f triple prime of 0, the third derivative, since the second derivative is 0, f triple prime of 0 is negative 1, okay, negative 1, okay, the fifth derivative of f at 0 is positive 1, okay, it's positive 1, and the seventh derivative of f at 0 is negative 1. So from there, you can see a certain pattern. Okay. Here, we already dropped all the terms that will be 0. So we are looking at the odd derivatives already. Okay. Now, let's obtain the Taylor coefficients. Okay. The Taylor, I mean, in this case, this is Maclaurin coefficient. Okay. So the Maclaurin coefficient would be this. So since this is first derivative, the Maclaurin coefficient for this is A1. So A1 equals f prime of 0 divided by 1 factorial, which is 1 over 1. So A1 is 1. Okay. While A3, okay, A3 is f triple prime of 0, okay, over 3 factorial. So that should give us negative 1 over 3 factorial. Let me just not write the factorial as as a single number. Let me leave it as 3 factorial. Let me leave the factorials as factorials. Okay. You'll see later why. Okay, so we'll have this as a5, okay, as the fifth derivative um of f at 0 over 5 factorial. So this is 1 over 5 factorial. And this one, um a7, okay, the seventh Maclaurin polynomial is the seventh derivative of f at 0, okay, over 7 factorial. So that gives you 1 over 7 factorial. Now, here are your Maclaurin coefficients. Here are your Maclaurin coefficients. So you have A1 equals 1 over 1 factorial. Okay, 1 over 1 factorial. A2 or A3, okay, as negative 1 over 3 factorial. A5 as 1 over 5 factorial. A7 as 1 over 7, negative 1 over 7 factorial. We wish to find AN, the general pattern for this. Okay. Now, number 1. Okay. Since we have already dropped out the odd terms, or the even coefficients of your including the A0. Okay. Including the A0. We already have dropped it out. Let us just simply look at this as let's simply look at this set of Maclaurin coefficients as it appears here. Okay. So without any consideration on the on the on the even terms, okay, of your Maclaurin series later on. Let us just look at finding the AN, considering these non-zero Maclaurin coefficients. Okay. So you see that this is an the given Maclaurin coefficients have alternating signs. Okay, starting with A1. Okay. So in that case, let's that factor negative 1 raised to n would appear. Okay, that negative 1 raised to n would appear. Now, um, since these are all odd terms, no? Pero we will consider this and this to be the odd numbered terms. Okay. I recognize the fact that these are all odd terms. Okay, but we still have to number this as term 1, term 2, okay, term 3, and term 4. So therefore, those those terms that are numbered as odd numbers are odd numbered terms. Okay. And you can see that the odd numbered terms um are positive, while the even numbered terms are negative. So in this case, negative 1 raised to n would work. Okay, because when n is an odd number, it wouldn't work because when n is an odd number, this becomes negative. Here we have here, okay, we have here a number, okay, a number that is ano, that we have the odd numbered terms such as this one and this one to be positive. This is negative when n is odd. Okay, so um, hmm, let us use here. Okay, let's try to use n plus 1 here. Okay, okay. So let's try to use negative 1 raised to n here. Okay, negative 1 raised to n plus 1 here. So that when you have, for example, a equals 1, okay, when you have a equals 1, you'll have um, 1 plus 1 squared, so that's positive. Okay. Here's what we're going to do, no? Here's what we're going to do. Despite that these are labeled 1, 3, 5, and 7, we'll consider these coefficients to be the coefficients when n is equal to 1, when n is equal to 2, when n is equal to 3, when n is equal to 4. Okay? And that is what I've been telling about this, this number. Okay? Um, we'll consider the coefficient a1 to be the coefficient when n is equal to 1, the coefficient a3 as the coefficient when n is equal to 2, and so on. Okay. That that's the reason why we actually drop those terms that are zero already. Okay, we will have to we replace them later on with these numbers 1, 3, 5, and 7 with this n, because we would like our summation to be written compactly as n equals something, say for example 1 up to infinity, which counts from 1, 2, 3, 4, 5, and so on. Okay. So, yeah. Now, let's look at the numerator. Okay, so the numerator is all 1, so we will have this the numerator is 1. And the denominator is 1, 3, 5, 7. Okay, factorial. Okay. Now, if we actually base your counting on these ends, okay, and not on the subscript, okay, and not on the subscript, we instead basing it here, okay, we would like to form an expression that would give us 1 factorial when n is 1, 3, okay, when n is 2, 5 when n is 3, and 7 when n is 4. Okay? And that number, okay, or that expression is actually 2n plus 1. Check. When n is 1, okay, when n is 1, 2n minus 1 pala. Okay, 2n minus 1. Okay. Since we would like our series to start at n equals 1. Okay. So when n is 1, okay, when n is 1, this is 2 minus 2 times 1, that's 2, minus 1, that's 1. When n is 2, this is 2 times 2, that's 4, minus 1, that's 3. Okay. When n is 3, this is 2 times 3, that's 6, minus 1, so that's 5. Okay. And when n is 4, this is 2 times 4, that's 8, minus 1, that's 7. So 2n minus 1 would give us this pattern, 1, 3, 5, 7. So we will have to take its factorial then. Okay. Now, how about so this is the end term for the coefficients. Okay. But how about forming the entire Maclaurin series. Okay. The Maclaurin series will then be written as this way. So f of x for your sine of x is we start with this one. Okay, so that's 1 times x. Okay, so that's 1 times x, so that's x, minus 1 over 3 factorial times x cubed, okay, plus 1 over 5 factorial times x raised to 5, okay, minus 1 over 7 times x raised to 7 factorial times x raised to 7, and so on. Okay. Now, the coefficients are already given here. Okay. What we just need to do, okay, what we just need to do is to multiply this with the powers of x. And as you can see, if this is 1, and this is your first term, this is your n equals 2, this is your n equals 3. As you can see, this pattern, okay, that 1, 3, the exponents actually follow the same pattern as that of your denominator here. Okay, so therefore, we can actually write the nth term of your series to be negative 1 raised to n plus 1 um, times 4x, this is x raised to 2n minus 1, and the denominator as 2n minus 1 factorial. Okay, so that the Maclaurin series that would represent your sign, okay, the Maclaurin series that would represent your sign is the summation, okay, of negative 1 raised to n plus 1 times x raised to 2n minus 1 over 2n minus 1 factorial for n equals 1 up to infinity. Okay, and this Maclaurin series is supposed to represent sine of x. Okay, it's supposed to ha. Linawin ko lang at this point that it is supposed to because number one, we don't know whether this series actually converges. And number two, even if this converges, we don't know if this actually converges to sine. Okay, if this actually converges to sine. So as of this point, this is supposedly, okay, so this is supposedly the power series that would represent, or the Maclaurin series that would represent your sine x. Okay, now, um, there may be a different interpretation for this one, most especially if you would start your series for n equals 0. Because when you start your series to be n equals 0, okay, when you start this to be n equals 0, your signs here will actually be different. Okay, say for example, if you're starting this to be n equals 0, okay, the power here should have been 2n plus 1. Okay, so if this is 1, that's 2 plus 1, 2 times 1 plus 3. Okay, and if this is 2. Okay, so it actually depends on where you would want to start your series. Okay, for example, I think the example here started at 0. Okay, so when it started at 0, okay, when it started at 0, it's n, the exponent of your negative 1 is simply n, not n plus 1. Okay, again, if you start at n equals 0, okay, when you start at n equals 0, uh, when you start at n equals 0, this is 0 for the first term, okay, which is positive, which makes your first term positive. Okay, um, and subsequently, all of the odd terms, okay, would be positive also, and all the even terms would be negative when you start at n equals 0. But when you start at n equals 1, this is what I had that I was what I was able to write out. The summation of negative 1 raised to n plus 1 times x raised to um, 2n minus 1 over 2n minus 1 factorial. Okay, well, this is now starting at n equals 1. Okay. Um, so when n is equal to 1, this becomes 1 plus 1. So that's an even number. So that makes it positive. Okay, so that is why for the first term, its first term would now be a positive number, which we were able to obtain as, yun na nga, this is, for n equals 1, this is 2 times 1 minus 1, so that's 1. Okay, so that's x, okay, over 2 minus 1, 2 times 1 minus 1, so that's 1 factorial, so that's over 1 factorial, so that's simply x. Okay, and then this is negative because this becomes 2. Okay, so 2 plus 1 is 3. Negative 1 cube is negative, so that's negative. This is 2 times 2, 4 minus 1, 3, so that's x cubed. Okay, and this becomes 2, same thing, this becomes 3 factorial, and so on. So I'd be able to generate the same series. Okay, actually, if you would check, um, you would have the same set of terms for each. Okay. Now, which is correct in this case. Since you are arriving, okay, you are arriving on the same or on the same set of terms for either for either series. Okay. Both are correct. Okay. This is just where you start, whether it's n equals 1 or n equals 0, is a matter of mathematical convenience. Okay, it's a matter of mathematical convenience. As long as you are explicit. Okay, you are explicit in saying, or you are blunt in saying that you're starting your series for n equals 1 or n equals 0. Okay. It won't matter. Okay. Although there are times that we really need to start at n equals 0. Okay. And we start at n equals 1. It actually depends on the context of the problem that we are dealing with. Okay. So I actually have, although the here's the thing. By definition here, your Maclaurin series actually starts as n equals 0. Okay. So we actually would have preferred to have written it this way. Okay. I just use, because this is already here. Okay. And you will be able to read this already. I just demonstrated to you. Okay. That where you start your series, 1 or 0. Okay. Would not really matter. Okay. Would not really matter. Okay. Um, as long as you are able to discern the pattern correctly. Okay. Because you would be able to arrive at the same set of terms. Okay. But at this point, we will strictly follow. Okay. If not stated otherwise, we would strictly follow that your series would always start at n equals 0. Okay. This basically is a more preferred This basically would be a more preferred answer for us rather than this one. Okay. But what I am pointing out here, uh, in this case that I am trying to show here is that um there may be variations. Okay, there may be variations that you would be reading in some books, because some books would show you that the Taylor series or Taylor polynomial, Taylor series for a for for your function would start at n equals 1, and some would actually have it at n equals 0. Okay. In our case, this is a more preferred this is a more preferred scenario. That is, we will start our series at n equals 0 unless it is really not mathematically possible for us to start at n equals 0. So when will that happen? That will happen if when our denominator becomes 0, when n equals 0. So in that case, we have no choice but to start at n equals 1. Okay? So if if division by 0 will not happen, if division by 0 will not happen, then we have to start our series for n equals 0. Okay, so again, by default, we will start our series for n equals 0. Okay, even if other starting points are possible. Okay, and we would only start with other values of n. For example, n equals 1. When starting at n equals 0 is impossible, such as when division by 0 would occur. Okay? So we prefer that your series would start at n equals 0. Now, what I was talking about earlier is that first question, will this series converge? Okay. So here, we have tested using ratio test, okay, whether that series would converge, and good thing it would converge at all values of x. Okay. So by ratio test, this ratio would actually give you a value of 0. Okay, it will give you a value of 0. So therefore, that would mean that the series would converge for all x. But again, we cannot conclude that the power series converges to sine x for all x. Even if this is convergent, if the series is convergent, we are not really sure. Okay, we are not really sure that this series would actually converge to sine x. Okay, at this point, we're not really sure that the series would converge to sine x. All we know is that the sum, all the series would converge to a sum. But we don't know if that sum is actually sine of x. Okay, so this is a subtle. Okay, remember that this is a subtle but important point in dealing with Taylor or Maclaurin series. Okay, for example, you can actually take a look at this series, uh, which can be, which can be, whose Maclaurin series can be that of what we have obtained in example 57. Okay, but this is a different function than f of x that we have used to derive that. Okay. Again, this is the Maclaurin series for this. Okay, the Maclaurin series for this is the same as what we will be able to derive for the Maclaurin series for sine of x. Okay. So at this point, we are not sure whether your series is actually converging to this or to this at this point. Okay. So how do we now tell if it actually converges to that to this one? Okay. Okay, how do we now tell? Okay. We can actually use the remainder theorem of the Taylor's theorem. I forgot what theorem number it is. Okay. So, but ayun, theorem 19 pala. Okay. So theorem 19, Taylor's theorem actually tells us about the remainder. Okay. Which writes the remainder in the Lagrange form. Okay. But the problem that we have been encountering with this remainder is that it requires us to know the value of z. Okay, it requires us to know the value of z, which what we only know is that it is between x and c. Okay, but we don't know its exact value. So what we were doing in that lesson in lesson 4.7 is that we were trying to find an upper bound. Okay, an upper bound for your error. Okay, we're trying to find an upper bound for your error, which basically ends up to be x minus c, x minus c raised to n plus 1 over n plus 1 factorial. That's the upper bound of your error. Okay, so if we can actually prove that your error or that your remainder approaches 0, we can actually say that your Taylor or Maclaurin series would converge to f of x. So if the remainder approaches 0, okay, then your this Taylor series would actually approach your f of x, okay, or would actually converge to f of x. So theorem 23 states that the power series formed with Taylor coefficients converges to the function from which it was derived at precisely those values for which the remainder approaches 0 as n approaches infinity. Okay. So the only way that we can be sure that our function or our series, our Taylor or Maclaurin series, would converge to f of x if the remainder of this Taylor polynomial would actually converge to 0. Okay, as n approaches infinity. Okay, but again, I'll raise again the problem that we were not able to determine the exact value. Okay, we were not able to determine the exact value for your remainder, but what we only have is its upper bound, which is this one. Okay, but here's the thing: if the upper bound of your error or if the upper bound of your remainder actually approaches 0, then we can be 100% sure that your error will also approach 0. Actually, that's by sandwich theorem. Okay? Since Rn, okay, is less than is less than this. Okay? Is less than this one. Okay? If we can be sure that the upper bound of your error, okay, approaches 0, or if the limit of this, okay, as n approaches infinity is actually equal to 0, okay, then we can be sure that the limit of r of n as n approaches infinity is also equal to 0. This is by sandwich theorem. Oh, sorry, sandwich. This is by squeeze theorem pala. Okay, so this is by squeeze theorem, we will be able to say that your remainder would approach 0 if its upper bound also approaches 0. That's by squeeze theorem. Okay. So now example 58 would now show you how to prove, okay, how to prove that the series we were able to obtain in example 57, this one, okay, actually approaches to sine x. Okay. So here we find that the upper limit, okay, of your the upper limit of your error is, or can be written this way. Okay. So it can be written this way, in which if we actually evaluate, okay, if we actually evaluate that if we can actually evaluate the value, okay, the value of your of your of this, the limit of this, if we evaluate the limit of this, okay, as n approaches infinity, okay, and prove that this becomes 0, which indeed it will become 0 because n factorial rises very rapidly. Okay, so this is an exponential over a factorial. We've been talking about this from the start. Okay, if you're taking the limit of an exponential over a factorial as n approaches infinity, okay, the factorial rises rapidly. So therefore, this will be the denominator will become a very large number, okay, as compared to the numerator at some large n. So therefore, slowly, this limit would actually approach 0. Okay? So, by squeeze theorem, theorem 3, okay, we will be able to see, or to say that if the upper bound of your remainder, um, if the limit of your upper bound becomes 0, then we can say that the remainder itself would actually become 0 as n approaches infinity. Okay. So by theorem 23, we can say now, since your Rn approaches now 0, okay, as n approaches infinity, we can now say that your sine x actually converges, or the power series, or the Maclaurin series for sine x, okay, actually converges to sine x. And that is for all values of x. Because we found that the Maclaurin series actually converges for all x. Okay. And this is the missing link now. Okay, this is the missing link. That is, we are now able to say that the Maclaurin series, number one, converges for all x. Okay, and number two, if it since it converges, it would actually converge to the function from which it was derived, which is sin x. Okay, so therefore, and that is because we have been able to prove that your remainder approaches 0. Now, this is an illustrative proof of that, of that assertion. Okay, if you actually graph the Maclaurin polynomials, okay, P1, P3, P5, and P7, those are in the sin x is in black, in black waveform. As you can see, as you increase the number of terms of your Maclaurin series, the shape of the polynomial, okay, the shape of the polynomial actually becomes more and more that of your sine function. Okay. So you can verify that if you actually add plus x raised to 9 over 9 factorial here, the shape of that of the graph of this is actually much more like your sine of x. Okay. Okay, so this graph actually demonstrates you that idea. Okay, so when you have your P1, okay, your this is simply a Maclaurin polynomial. Okay, so when we use a single term of your Maclaurin polynomial, you'll have that one. But when you have two terms of your Maclaurin polynomial, okay, when you have 3 terms of your Maclaurin polynomial, 5 terms, okay, and 7 terms. So as you can see, the polynomial, as you increase the number of terms, okay, as you increase the number of terms, you'd be seeing that it is more, um, it is shaped more and more like that of the sin x function, okay? And that is how that is the illustrative proof of the, that is the illustrative proof of the convergence, or that um your polynomial, or your series, your Maclaurin series would actually would eventually converge to your sine function. Okay, so that's an illustrative proof of the convergence of your Maclaurin series converging to your sine function. You can actually find partial sums. Okay, partial sums of your Maclaurin series. Okay, and then try to see and plot them. Okay, and try to see if if these partial sums eventually, okay, would converge to your function. Okay, so that. So these are the guidelines for finding a Taylor series. These are actually the same guidelines that we have been using for finding Taylor polynomial. The the only difference is that we need to find a general term for that. Okay, we need to find a general term. Okay, for an. Okay, but and also after finding the interval of convergence, we need to determine whether the series converges to f of x. Okay, how do we determine that? We need to find whether Rn approaches 0. Okay, and since this would be impossible for us to do, okay, this would be impossible for us to do, we can resort to finding whether the upper bound of Rn actually approaches 0. And it's usually, it's x minus c raised to n plus 1 over n plus 1 factorial. Usually, okay. But there are cases that this is not the case, no? There are scenarios that this would be not the upper bound for your R of x. So, um, you'd actually be we would be cognizant of that if if your Rn, if the form of your Rn, which is supposedly the n plus 1 derivative of z over n plus 1 factorial times x minus c raised to n plus 1 would actually have a different form, especially for this one. Okay? So far, for the three examples that we had, okay, three examples, two from 4.7 and one from this example, the previously concluded example. We had all the upper bound of your of your Rn to be this. Okay? So you notice the form of this in all of these three cases, and see that the explanation for this to be being the upper bound is that this is actually the maximum value that Rn can actually take. Okay. If you can remember, in the first case, in the first two cases, we had this value. We have the value of this to be less than 1 for the range given for z. Okay. For the range given for z, the value of this is less than 1. So if we actually multiply this, okay, if we actually multiply this, even if we know z, we would know that it would just lessen the value of this one. So therefore, we just ignore that. Okay, rate that as equal to 1 and treat this to be the upper bound of the error. Okay. In this case, what happened was the nth derivative of your say being f of x as sine x. The n plus 1 derivative of z would either be cosine or sine. I mean, either positive cosine or positive sine. In which case, the maximum and the minimum value of that is positive 1 and negative 1. So therefore, that still justifies the use of this as the upper bound for your error. Okay. So there. Um, the direct determination of Taylor or Maclaurin coefficients using successive differentiation can be difficult. Okay. And the next example illustrates a shortcut for finding the coefficients indirectly. Okay. But that would start from the coefficients of known Taylor or Maclaurin series. Say, for example, we would like to find the Maclaurin series for sine x squared. Okay. If you do successive differentiation, you would have something like that, which is really cumbersome. Okay. And the fact that the thing about f of x equals sine of x, the thing about its Taylor series or Maclaurin series is so elegant. It's because its derivative are actually repeating. Okay. So that we are able to generate a number of terms that allowed us to actually find a general pattern. Okay. In some cases, that would not be possible because like this. Okay. Even if you are able to find all the derivatives and substitute the center of this, which is 0, you might not be able to find a pattern for all of the numbers that you will be able to find. Okay. But what we're going to do here is this. We'll do function composition. Okay. We will compose a new function. Okay. From a given function, we will compose this function. Okay. So how do we do that? First we consider. Okay. We first consider that your sine x, okay, has this as your Maclaurin series. So you have it as x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial, okay, minus x raised to 7 over 7 factorial, and so on. Okay. Now we will compose, okay, we will compose your function this way. Since we're looking for sine x or sine of x squared. Okay, since we're looking for sine x squared, then we'll let x equal x squared. So therefore, let's have sine x squared equals, this is x squared minus this is x raised to 6 over 3 factorial plus x raised to 10 over 5 factorial minus x raised to 14 over 7 factorial, and so on. So that would be your Maclaurin series for sine x squared. Okay, but again, two questions. Does this function really converge? Okay. Number two, if this converges, does this converge to sine x squared? So we have to answer those two questions pa. Okay. So be sure to understand the point illustrated in example 59. Okay, because the direct computation of Taylor or Maclaurin coefficients can be tedious, the most practical way to find a Taylor or Maclaurin series is to develop power series for a basic list of elementary functions. This is what I have been pointing on the previous lessons. For us to expand, okay, for us to expand the functions that we will be able to write a Taylor or Maclaurin series of, we need to develop a table for or a list of the Taylor or Maclaurin series for some elementary functions. Okay. So from this, we can determine the power series for other functions by addition, subtraction, multiplication, division, differentiation, integration, and composition. Okay. So that's the approach that we would like to do here. Okay. But before you do that, this example would actually demonstrate how to develop what we call a binomial series. A binomial series is a series for a binomial term, a power series for a binomial term. So that binomial term is 1 plus x. Okay. So the powers of that would be obtained by raising that binomial term, okay, or that binomial factor into a power. Okay. So in that case, if you try to find the if you try to find a Taylor or Maclaurin polynomial for that, you would have to do successive differentiation, okay, which would produce this series, okay, and verify that this is convergent in the interval -1 to 1, okay, with a radius of convergence of 1. This is actually useful for functions containing radicals. Okay, because basically this power or this binomial expansion would actually work for fractional values of k. This would work fractional powers of or fractional values of k. By the way, it was stated here that k is not a positive integer. Okay, it was explicitly stated there that k is not a positive integer. So this binomial series would actually we would actually use this for for um for your function having radicals. Okay, because k here is actually understood to be fractional. So note that example 60 shows that the Taylor series of this converges to some function in the interval negative to 1 to 1. However, the example does not show that the series actually converges to x plus 1, 1 plus x raised to k. Okay, so we were not able to prove, but without proof, we will be stating bluntly, okay, that this series actually converges to this. Okay, so here is an application of that. Okay, so as you can see, you have here a function that contains a radical. In this case, k is 1/3. Okay, so we use that series, we use that binomial series, okay, to write a binomial expansion for a power series expansion for this one. Okay, by letting k equals 1/3. So we have this. Okay, so here 1 and then 1/3 x, then 1/3 minus 2 1/3 times 2/3. Okay, so that's negative, then multiply to 2, so we have this. Okay, and then and so on. Okay, so um should be able to verify, you should be able to write this. You should be able to write this series, okay, from this by setting k equals 1/3. Now you should be able to check, okay, you should be able to check whether this series actually converges for if it converge, this series is known to converge from -1 to 1. Okay, exclusive, it means it doesn't include yet -1 to 1. Okay, but you have to prove that it actually converges on endpoints, which in this case it would. Okay, and of course, without proof, we were able to, we will just simply state that this series, okay, this series would actually converge into this. Okay, so there. Now, I have listed here, okay, I have listed here values of various functions and their um Taylor or this is basically a list of Maclaurin series. Okay. This is a list of Maclaurin series, if I'm not mistaken. Okay. But you can actually you can simply you can simply change this to a Taylor series. Say for example, if you have this e raised to x, and then you would want it to be centered around, say for example, x equals 2. Then you can simply change x here to x minus c, or x to x minus 2. And then you can have your Taylor series centered at 2. Okay? So there. That's how we use this list. Okay? And again, we can be able to derive more and more Taylor and Maclaurin series for other functions by doing some operations on this known series. So say for example, you have here, okay, f of x for cosine of square root of x. So this is function composition. This is simply function composition. We start with cosine of x and its series, which is the sum of -1 raised to n, x raised to 2n over 2n factorial for n equals 0. I think this starts at 0. Okay, and to infinity. Okay, I I think all of this actually starts at 0. Okay, all of the series are do start at 0, except possibly all of them start at 0. Okay, so that. Now, what we will do is we will replace x here with square root of x. So we will have to replace this x here with square root of x. Okay, so which means that cosine of square root of x would be just simply the sum of -1 raised to n multiplied to square root of x raised to 2n, okay, over 2n factorial for n equals 0 up to infinity, which is when you simplify this, simply becomes the sum of negative 1 raised to n x raised to n, okay, divided by 2n factorial for n equals 0 up to infinity. So this is now your Maclaurin series for cosine of square root of x. Okay. And again, you have to verify whether number 1, this actually converges. Okay. And number 2, okay, this actually converges to cosine of square root of x. Okay. So those are the things that you have to prove after this. Okay. So we just stated it here without proof, but you have to prove it. When for your quizzes and your assessments, you have to prove that assertion that they actually converge to that. They're actually convergent and they actually converge to square root of x. Okay. So again, test this. This is a power series. So to prove that this converges, you test this using ratio test. Okay. And to prove that this actually converges to cosine of square root of x, you have to prove that your Rn approaches 0. Okay. So here, okay, you have here a product of e raised to x and arctangent of x. Okay. So here, this is the series for e raised to x. And here's the series for arctangent of x. Obtained from the table above. Okay. So by multiplying those two, okay, and of course, you combine the like powers later on, you would be able to get the power series for the product. Okay. Same thing with tangent. We know the tangent is sine x over cosine x. Okay. And this is the power series for your sine x. This is the power series for your cosine x. By long division, okay, by long division. When you do long division, you divide the first term to the first term. That's the idea here. You divide the first term to the first term. Okay, so when you do long division, the quotient here would become the first few terms of your um the first few terms of your uh power series for tangent of x. Okay. Now, here in example 64, instead of actually doing it this way, finding the product sin x over sin x, which is okay. Okay, I'm not saying that this is wrong. Okay, you can actually make it easier. Okay, by actually writing sin square x in terms of cosine, which is now not a power function, not a power function for cosine, but rather just a product of a product of angle. Okay. So as much as possible, you avoid powers for your trigonometric function as much as possible. Okay. But if that is not possible, then you can proceed as in this one. Okay. But here, an easier way to do this is to actually make it or to write this in terms of cosine. Okay. Now start with the series for cosine x, replace x with 2x, okay? Replace x with 2x, and then you add or you multiply the entire cosine 2x series with negative 1 half, and then you add 1 half to the series. So you'll get the series for sine square x. Okay? Again, check if this is convergent, okay? And check if this is converges to sine square x. Okay? Power series can also be used to obtain table of values of transcendental functions, especially if you cannot really evaluate that transcendental function by hand or by analytic means. Okay. For example, this integral is actually one of the most used integral in statistics. Okay. Uh, in stat, okay, this is one of the most used integral that you can encounter. And before that, your calculators cannot perform um, calculations for the or approximations for this integral. What statisticians did was to create table of statistical values. Okay, if you were able to study in your statistics before, the Z value, okay, areas under the curve, area under the curve, okay, of a normal distribution. Sorry, areas under the normal distribution curve. Yun, that's the correct name for that. Area under the normal distribution curve, which basically is is your Z, is related to your Z value. Remember Z test? Okay. If you are able to study this in the statistics, this normal distribution curve is actually this curve. Okay, this e raised to negative x squared curve. Okay. So what you would like to do here is to estimate the value of this. Okay, or approximate the value of this. Okay, which it's actually it's integral. Okay, from negative infinity to positive infinity. Is actually known to be 1. Okay. It's actually known to be 1. Okay. But if you want to just determine it from 0 to 1, okay, you'd be able to to use the Taylor series for e raised to x, starting from the Taylor series of e raised to x. Okay, and then replace x with x squared or negative x squared so that you can have this alternating series. Okay. And then integrate this term by term. So you'll have something like x minus x cubed over 3 plus x to the fifth over 2 factorial times 5 and so on. Okay. Now, using the first 1, 2, 3, 4 terms, using the first four terms, okay, you can estimate the value. Okay. You can estimate the value to be 0.74. Okay. And if you're asked for the error, okay, if you're asked for the error, this is actually the maximum value of the error for your approximate value of 0.74. So by basically that's Taylor's theorem. This may be the first few terms of your approximation polynomial. The rest of this one, the immediate term after after the last term that is used to approximate this is actually the error. Okay, so that would be the approximate error there. So your approximate error is 0.005. Okay. I think I can let us test if your calculator can actually evaluate this already. Because that's the problem before. Your calculators cannot evaluate problems such as this one. So that is why there are statistical tables. Okay. So here, okay, we will let me attempt to do that. So that's e raised to negative x squared from 0 to 1. There. It can evaluate 0.74, 68 something. Okay. So there. That's how that's the um that's how we can actually use your Taylor series and Taylor polynomials in order to make approximations. Okay. And that is actually the idea behind this series. Okay. We are studying infinite series to represent functions, but basically these infinite series are used, okay, to approximate the values of these functions, okay, especially in numerical computations. So, and that is why you can find this lesson in in conjunction with some of your activities, namely activity 4. Okay. So Taylor polynomials are discussed also in activity 4 as to how we discuss it here. Okay. So and then from in that in that activity you'll be able to use computers in order to verify, so for example Taylor's theorem. Okay. So that ends our topic on infinite series. Okay. So now as of this point, if you're able to master, if you're able to master these concepts about your uh, about your infinite series, we should be ready now to use this idea, okay, to use this idea in order to solve differential equations, okay, using the power series method, which we will do in topic number 5.